Hello everyone, I'm Guo, and I'm from the University of Haifa. In this talk, I'm going to tell you something about deterministic polynomial factoring over finite fields with linear Galois groups. And the subtitle says this is an additive combinatorics approach, but most of the talk will be focusing on polynomial factoring itself. Like I will explain the status of the problem or the general ideas of the problem. And at the end of the talk, I will try to explain how additive combinatorics comes into play. So let's get started. We are interested in the problem of univariate polynomial factoring over finite fields. Here we are given a univariate polynomial fx defined over a finite field fq, and by scaling, we may assume the polynomial fx is monic, meaning that its leading coefficient is 1, and let n be the degree of this polynomial. And we want to output the factorization of fx into irreducible factors over the finite field fq. And this problem is a very basic problem in computer algebra. And it's used as a subroutine in many problems from different areas. For example, it's used in multivariate polynomial factoring over finite fields, and constructing error correcting codes, and designing public key crypto systems, etc. So you may think that for such a basic problem, people must have already found efficient algorithms solving it. Well, this is partially true because we do know several randomized polynomial time algorithms. For example, we know Euler-Camp's algorithm, which is one of the earliest algorithms, randomized polynomial time algorithm, and we also have the algorithm given by Cantor Zassenhaus and the one given by Galois and Ullmanns, and they have different time complexity, but they all run in randomized polynomial time. On the other hand, the problem of finding a deterministic polynomial time algorithm still remains open, even under standard number theoretic hypotheses, like the generalized Riemann hypothesis or GRH. Euler-Camp, besides giving the randomized algorithm, he also gave a deterministic algorithm that runs in time polynomial in n, log q, and p, where p denotes the characteristic of the finite field. In particular, if p is polynomially large, then the algorithm does run in polynomial time, and this is often sufficient for many applications. However, in general, p could be exponentially large, so this algorithm could still run in exponential time. And Shoup gave an algorithm that runs in deterministic time square root of p times poly n log q, and this algorithm was later slightly improved by Berger and other people. And again, this algorithm could take exponential time in the worst case. And believe it or not, this is already the best known time complexity that we know, unless you are willing to assume hypotheses like GRH. If we do assume GRH, then there is another algorithm given by Evdokimon that runs in deterministic time polynomial in n to the log n log q. So this is a quasi-polynomial time algorithm, and this algorithm was later extended by Ivanyos-Karpinski-Saxena, or IKS, and I will get back to this algorithm later. There is another approach in the literature which I call the Galois theoretic approach. In this approach, the input polynomial fx is assumed to be defined over a prime field fp, and besides fx, we also assume a lifting polynomial f tilde x is given whose coefficients are integers. It's a lifting polynomial in the sense that the residue of f tilde x modulo p equals fx. People have observed that the problem of factoring fx becomes easier if you are given this lifting polynomial f tilde fx, and the Galois group G of f tilde x has some special structure. This is because if you are given this lifting polynomial, then this gives a way of efficiently computing a group of automorphisms acting on certain algebra, and it turns out that these automorphisms are useful for polynomial factoring. So people have obtained the following algorithms in this Galois theoretic approach. Huang in 1984 gave a deterministic polynomial time algorithm for the case that Galois group is abelian under GRH. And Evdokimon extended this result to the case that G is solvable. Ryan gave an algorithm that works for an arbitrary Galois group G, but its time complexity is polynomial in the order of G, and the size of the input. So in the worst case, the Galois group could be the full symmetric group. This is actually also the typical case. And in this case, the Galois group has order n factorial, which means the algorithm could still run in exponential time. So to summarize, we have a deterministic polynomial time algorithm under GRH when given f tilde when G is solvable. And in general, we also have an algorithm that for arbitrary G, but its time complexity could be exponentially large. Recently, in a previous paper, we were able to extend the Galois theoretic approach by combining it with the ideas in Evdokimov's quasi-polynomial time algorithm and its extensions in IKS. Here is the main theorem that we proved in that paper, stated informally. We showed that assuming GRH, there is a deterministic algorithm that, given the lifting polynomial f tilde x, factorizes fx in time polynomial in log p and the complexity of the Galois group G of f tilde x. Here the complexity of the Galois group G is a measure that measures how complex the group G is. I won't give the formal definition, but let me just point out that when G is a symmetric group of degree k, or more generally a subgroup of symmetric group of degree k, then the complexity of G is bounded by a polynomial in k to the log k. Therefore, the running time of the algorithm in this case is at most polynomial in log k to the log k and the log p. And if G is a subgroup of symmetric group of degree k for k up to 2 to the square root of the log n, then the algorithm runs in polynomial time. So this is a generalization of the results of previous results in the Galois theoretic approach. And so this is for symmetric group. And one natural question is how about other families of non-solvable groups, for example, general linear groups? In this talk, we will be focusing on what we call linear Galois groups, including general linear groups and their subgroups. Here are the formal definitions of linear groups and linear Galois groups. Suppose V is a finite dimensional vector space defined over a finite field, and S is a subset of V, and G is a subgroup of the general linear group GLV acting on the set S. We say G is a linear group if its action on S is induced from the standard action of the general linear group on V. So linear group is not just an abstract group, it's a permutation group on a set S. Now given the lifting polynomial f tilde, we say its Galois group G is a linear Galois group if this group as a permutation group on the set of roots of f tilde is a linear group. And here's the main theorem in this talk. We show that suppose the Galois group of f tilde is a linear Galois group and acting on the set S of roots of f tilde, and the number of the cardinality of this set S is at least the size of V to some constant power. Then we show that given the lifting polynomial f tilde, the polynomial fx can be factorized in deterministic time polynomial in n to the m and log p, assuming GRH, where m is given by this it's O log n divided by log n to the 1/3. So this means if we are given f tilde with a linear Galois group, we can slightly improve the time complexity of Evdokimon of the algorithm, which runs in time polynomial n to the log n times log p. In this case, we can do slightly better, and this improvement was not known before, and the improvement is kind of embarrassingly small, but we believe that it can be improved. And the reason it's so small is not due to the nature of the problem, but more likely due to our proof. To explain our ideas, I first need to explain Evdokimov's quasi-polynomial time algorithm. So to explain Evdokimov's algorithm, let's first assume we are in a special case where the polynomial fx splits into a product of distinct linear forms over a prime field fp. And this assumption is fun because in the literature there exists deterministic polynomial time reduction from the general problem to this special case. Then we define a ring R as follows. So we introduce a new variable y and define R to be fpy, the polynomial ring fpy modulo fy. Then instead of factoring fx over fp, let's factor it over the ring R. Of course, factorization over R is not equivalent to factorization over fp, but people have observed that if we get good enough partial factorization over R, then such factorization projects to a non-trivial partial factorization over fp. In particular, if we get a complete factorization over R, then it projects to the complete factorization of fp. So one way to get a factorization of fp is to first lift to the algebra over R and compute the factorization over R, and then project it down to get the factorization of fp. And I want to remark that this lift and project method is also used somewhere else in theoretical computer science. For example, it's used in the classical Weytsfehler-Lehmann algorithm for graph isomorphism testing. You may wonder what's the advantage of working over the ring R instead of over fp. It turns out that it's easier to factorize fx over R for the following reason. When we define the ring R, we introduce a new variable y. Therefore, we are working with the algebra that has two variables x and y, and this algebra has an efficient computable automorphism sigma that exchanges the variables x and y. And as I mentioned before, efficiently computable automorphisms are good for polynomial factorings. And in particular, Ryan showed that if you have this automorphism sigma, we can use to efficiently compute a non-trivial partial factorization of fx over R. And Evdokimon used this observation to prove the following lemma. He showed that there is this deterministic polynomial time algorithm under GRH that computes either one of the following. So we could either compute non-trivial partial factorization of fx into at least two factors, the product of two factors over fp, or we could compute a non-trivial partial factorization of fx into the product of f1 and f2 and the linear factor x minus 1 over the ring R, where the degree of f1 and f2 are equal, and they equal the degree of f minus 1 divided by 2. And also here in the second case, we could assume the degree of f1 and f2 are greater than 1, because if they are equal to 1, then we have the complete factorization. And as I mentioned before, in this case, you could project the factorization down to get a factorization over fp. So we are in this case, we are reduced to the first case. When we are in the first case, we get a non-trivial partial factorization of f into at least two factors, and then we can solve the problem recursively by further factorizing f1 and f2. The problem is the second case. In this case, we get a non-trivial partial factorization over R, but it does not necessarily lead to any non-trivial factorization over fp. So not all partial factorization over R projects down to non-trivial factorization over fp. So what do we do in this case? In this case, we need to refine the factorization. So we need to further factorize f1 and f2 over R. The next observation is that the problem of factoring fx over R is just like the original problem of factoring fx over fp, except that fp is replaced by R and fx is replaced by the new polynomial fx, and the degree of fx is less than half of the degree of fx. This means we could solve the problem recursively. That is, we introduce a new variable z and define a ring R prime, and then we factorize fx over R prime using automorphism, exchanging the variables x and z, and so on. We continue this process. Each time we add a new layer to the recursion tree, the degree of the polynomial that we are factorizing is reduced by at least a factor of 2, and the dimension of the algebra that we are working with is increased by a factor of at most n. Because we start with a polynomial of degree n, we can have at most log n layers, and the algebras we are working with have dimension at most n to the log n. So the algorithm runs in time polynomial n to the log n and log p. So to summarize, the reason Evdokimon's algorithm has time complexity polynomial n to log n and log p is that the number of layers in the recursion tree is log n. If we could reduce this number of layers in the recursion tree to little log n, then we could reduce the time complexity of Evdokim's algorithm. And if we could reduce the number of layers to constant, then we can get a polynomial time algorithm. I also want to mention one extension of Evdokim's algorithm by Ivanyos-Karpinski-Saxena, or IKS. So in Evdokim's algorithm, each time we introduce a new variable and then we use the automorphism that exchanges two variables. The idea of IKS is that instead of introduce variables one by one, we introduce all of them simultaneously. And say we have m variables, then we use the whole group of automorphisms permuting these m variables. And this group is the symmetric group of degree m. And the intuition is that because we have a larger symmetric group, a larger automorphism group, the hope is that we could show that for some smaller m, it's sufficient to factorize the polynomial fx. And in fact, IKS even conjecture that choose m to be constant is good enough. Unfortunately, so far it's not known how to show that choosing m to be little log n is sufficient. If one could show that choosing m to be a little log n is good enough, then it will improve Evdokim's algorithm. Another contribution by IKS is that they proposed the notion of m schemes, where m denotes the number of layers in the algorithm. This is a combinatorial structure which extends the notion of association schemes in algebraic combinatorics. So IKS showed that m schemes can be used to analyze their algorithm. Basically, they show that their algorithm always produces an m scheme, and whenever the algorithm fails to factorize the polynomial fx, then this m scheme must satisfy very special properties. So if we could rule out the existence of these special m schemes, then we can show that the algorithm by IKS always successfully factorizes the polynomial. Therefore, this reduces the algorithmic problem of polynomial factoring to the combinatorial problem of proving special m schemes do not exist. And analysis in Evdokim's paper and the paper by IKS boils down to show that special m schemes do not exist for m of order log n. And if one could show that if one could improve this bound to little log n, then we would have a faster algorithm. Again, no such bound is known so far. So finally, I'm going to talk about our algorithm. Our algorithm is very similar to the one in IKS. One main difference is that IKS works with this ring, which is algebra OFP, and we work with a different ring, which we call O bar, and it's defined in terms of the leading polynomial of tilde x that we are given. Also, IKS uses automorphisms that exchange the variables xi, and in our algorithm, the efficiently computable automorphisms come from the Galois group G of the leading polynomial f tilde. In this talk, we focus on the case that the Galois group is a linear Galois group. For simplicity, let's assume it's the full linear Galois group, general linear group. Then it can be shown that the automorphism group we obtain is a general linear group of rank m over a finite field, where m is the number of layers of the recursion tree associated with the recursive algorithm. We observe that our automorphism group is larger than the one used by IKS because the order of our group is at least 2 to the omega m squared. On the other hand, IKS uses the symmetric group of degree m. Its order is m factorial, which is 2 to the theta m log m. So as a result, we show that because of this, we show that choosing m to be little log n is sufficient. So this gives the algorithm that is faster than the Evdokimon algorithm, but only under the assumption that we are given the lifting polynomial of tilde whose Galois group is a linear Galois group. To prove the little o log n bound, we introduce something called the linear M schemes, which strengthen the notion of M schemes used by IKS. And here's the definition of linear M schemes. It's very technical, so I'm not going into details. But basically, there's a finite subset S, which is a subset of vector space V, and there's a collection pi of partitions P1 through Pm, where each Pi is a partition of the S-fold Cartesian product S to the I. And we say pi is a linear M scheme if it satisfies some conditions, and we also have a definition of special linear M schemes, which I'm not giving here, but the bottom line is that we could show that special linear M schemes do not exist for sufficiently large M for the little o log n, and this implies what we want. And interestingly, the proof uses tools from additive combinatorics like the Feynman-Ruza theorem, the Balog-Stemmer-Galois theorem, and some free analysis, etc. Here is an oversimplified overview of the proof. We maintain a partition P of the set S that comes from the linear M scheme, and we consider a set B in the partition whose cardinality is greater than 1. The argument used in Evdokimon algorithm is as follows. It can be shown that every time M is increased by 1, the set B is replaced by a new set B prime, such that the cardinality is reduced by at least a factor of 2. This implies that M is at most log n. And we could show that if we consider linear M schemes, then every time M is increased by 1, the set B is replaced by a new set B prime, and the cardinality is reduced by a super constant factor. And this implies that M is at most little log n. So we could show that each time the cardinality of the set is reduced by a super constant factor. And our proof for this fact is very complicated. I don't have time to get into details, but basically the proof is done by divide and conquer. We look at the sum set B plus B and divide the proof into 3 cases depending on how large the sum set is. And the first case is when the cardinality of B plus B is close to the cardinality of B. This means B is approximately a subgroup or a coset of subgroup of the vector space V. And the second case is when the cardinality of plus B is close to the square of the cardinality of B. This means B is close to what people call a Seidel set in additive combinatorics. The last case is the case between the previous 2 cases. So the cardinality of B plus B is much larger than the cardinality of B, but much smaller than its square. And it turns out that the first case is the most difficult case, and it's also the bottleneck of the proof. So if you want to improve our result, you just need to focus on the first case. Finally, let me give you some open problems and future directions. So the first question is improving our little log n upper bound, or more specifically this upper bound. Our results improve the log n bound, but the improvement is very small. So we believe it should be possible to further improve it. And the second question is how to simplify our proof. Our proof is very complicated if you read the paper. So we wonder if there are simpler proofs. And finally, the last question is how to prove a little log n upper bound for M schemes instead of linear M schemes. And this is a big open problem. If one could prove such an upper bound, little log n upper bound, it would imply the existence of a deterministic algorithm under GRH that is faster than the Evdokimon algorithm. And if one could even prove a constant upper bound for M, it would give a deterministic polynomial time algorithm under GRH for polynomial factoring over finite fields. Okay, that's the end of the talk. Thank you for your attention.